Okay, this lecture is the crux of the series. So far, we made one conjecture, and it's only a partial conjecture, it's not a full conjecture, because we have evidence for it. So, we've got a potential structure for the most primitive level that we can get to. Now, if this is valid, we've resolved many problems in a kind of package without having to consider them separately. And we've not brought into it any new equation, exactly what we would expect. So what we want to do now is to find the mathematical basis behind this structure, if we can find one. And in the last lecture we got to 3 dualities between 4 parameters, which appear to be fundamental. And these dualities seem to be very close to exactness, if not precisely exact. You can find duality of that kind in mathematics throughout the whole of mathematics. Mathematics is riddled with duality. If we find it in physics, it seems to suggest that mathematics and physics might be closer than we previously thought. And what I'm saying here is that the abstract dualities are responsible for characteristics that we previously thought were physical, purely physical, so tangible things, but they're in fact purely abstract. Those were the dualities. You see, each pair of parameters is paired against a different pair each time, mass and charge, space and time, and so forth. These dualities, the signature in physics is a factor 2, and factor 2 and factor half are very common in physics, half mv squared, etc., half kx squared, lots of halves, half spin, 2s and halves everywhere, and nearly every time they're one of these dualities. And in fact, it's very interesting that this factor doesn't depend on particular dualities, just duality. A perfect example of this is electron spin half, which goes with the doubling of the observed magnetic moment. So what is this? Is it quantum, is it relativistic, or is it something else? Well, in fact, it's anything you want. It's all of them and none of them. So if you do it using the standard derivation from the Dirac equation, using commutators, that's effectively anti-commutativity of the momentum operator, which generates the factor. So that's that duality, the one about commutative and anti-commutative. If you do it in the first way it was ever done, the first explanation that was ever done was the Thomas precession, which was a relativistic correction of the frame of rotation. In other words, that's a different duality, but you don't need to use those, you don't need to use either quantum mechanics or relativity to do it. You can actually do it classically. You can do it by using the kinetic energy equation and the potential energy equation for standard potential and kinetic energy equations. Kinetic energy equation for changing conditions, basically half mv squared, potential energy mv squared for steady state, connected by the virial theorem v equals 2t. And if you use the kinetic energy at the very moment when you switch on the magnetic field, then it works perfectly. You can just use a very standard, almost trivial equation. You can use the old kinematic equation, v squared equals u squared plus 2as to do it. So we've got at least 3 different dualities. That's the Dirac equation, that's the Thomas precession, and that's classical kinetic energy, that's conserved and non-conserved. So none of these are the unique explanation. All are true, but none is uniquely so. And everywhere where this phenomenon of the factor 2 occurs in physics, it's got multiple explanations of this kind. Okay, now we come to the very important crux of all this work. Some symmetry seems to be at work between the fundamental parameters. What is it? Well, the best way to find out is to arrange the properties in a table. And we can see, if we look at that, that's got the structure that we presented in lecture 2. If I replace the properties and anti-properties by algebraic symbols of this kind, we can see that we've seen that before. We said that if we had properties arranged like that, we could represent a group structure if we set up binary operations of this form. So any combination of a single property or anti-property itself gives the property, but a combination of property with an anti-property gives the anti-property, like so. Fairly similar to multiplication rules. And then if it's with a completely different property, then it doesn't count, it's 0. And in fact, this is the Klein 4 group, the non-cyclic group of order 4. And that's its multiplication table. D2, dihedral 2, because it's also the group of the rotations of the rectangle. So that's dihedral 2. There are only 2 groups of order 4. There's a cyclic one and a non-cyclic one. And again, we know that it's got the property of this H4 algebra, where you've got double quaternions. So it's got the same representation as this group of quaternions. So interestingly, we're seeing not only has it got a group structure, but it's quaternionic in some way. It's not the only way it's quaternionic. The representation isn't actually unique. Very few things are at this level. On our first arrangement, we made mass the identity element. We made mass the identity element. The one with no minus signs is the identity element. But it needn't be. We could have made something else the identity element. We can rearrange the symbols. Their space is the identity element, and then the group table would look different. It would look like that. So any element could be the identity element, none is unique. Now if this representation is true, then we can no longer carry on doing physics as though it didn't exist. It's got to be a very significant way in which we will do physics afterwards. So once we've decided, if we do decide, that this structure is a true one, then we can never again look at physics in the same way. We've got to go through this method at this level. And if we do so, then we would expect it to be a powerful tool for new physical information. My own experience is that this is an exact symmetry. I have not found any deviation from it over a very long period of investigation. And I will hope to show a bit later on that the partial conjecture that was made in deriving it can now be justified by the results. We can actually show where it comes from. Also, another aspect of this concept is that we would expect it to be exclusive. If we're going for a totality 0, quaternionic structure, group structure of this kind, perfect symmetries, perfect dualities, then nothing else can be expected to disrupt this pattern. We would expect it to be exclusive. If it's exclusive, that gives us an extra constraint in which we can apply to physical situations, which is a very powerful concept. Very similar to the sort of constraints we have due to conservation laws. Conservation of energy provides a powerful constraint. This would provide an even more powerful constraint. We would then expect to be able to start deriving physical laws and physical properties and physical structures from this alone, without any extraneous information. Now, I don't say that will be easy. It's going to be very difficult, because you've got to develop complex models in which it applies, and it would take a lot of ingenuity. But one would expect to be able to do it ultimately. And of course, we've got a binary operation between the group elements, but it doesn't have to be that operation, it could be a different one. I can suggest another one immediately. Simple multiplication. Simple relationship between a numerical value of one quantity and a numerical value of another. After all, we've got built into this, we've got a quaternion structure in which 2 parameters are related numerically, and we've got a 4-vector structure in which 2 parameters are related numerically. So we would expect numeric relations between all of them. This group is particularly interesting because each parameter is its own inverse. Remember, one of the aspects that a group must have is that each parameter must have an inverse, and there must be an identity element. Any one of them could be the identity element, and each parameter in this group is its own inverse. And that's very interesting for many reasons, because it means that if we've got a numeric relationship between 2 elements, we should also have numerical relationships between elements of their inverses. And in fact, this is what we find occurs in string theory, for example, There are three well-known dualities in string theory, ST and U dualities, and which are very similar in concept to this idea of inverse relationships. And these conditions would be satisfied if we could find a unit for each parameter. A unit for each parameter would relate the parameter to its inverse. And we do have such units. We have the Planck length, the Planck time, the Planck mass, and the Planck charge. And of course, the units from which these are constructed, these objects, are completely meaningless. They're just, as I say, they're just the result of having Babylonian astronomers and French revolutionaries. They're nothing to do with anything fundamental. These are not fundamental constants in the way people think. They're just expressing our system of units as it developed historically. If there were fundamental constants, these are the ones. Okay, also we notice the importance of squaring in the algebra that creates them. Now the squared values of the parameters do have physical significance. We know space and time are important in Pythagorean and vector addition. And we know that in mass and charge, we know that they're important in interactions. So squaring is a very important aspect of these parameters. And interestingly, non-conserved parameters square undefined units, just anything. Whereas these square particular units. Interactions are between identifiable units. These are just between any units. If you see what I mean. Interaction between two particles is between two particular charges, two particular masses, two particular something. But if we're measuring space and time, but we're not actually using particular pieces of space and particular pieces of time in the same way. That's because of the conservation property. We can also create new composite quantities, and this is what we do in physics. And we can additionally express aspects of these that are characteristic, like invariance and variability, dimensionality and so forth, real and imaginary nature. And the reason why we do this is because the parameters only come as a package. They're not separate things. We can't separate one from the rest. They're all a package. It's all or nothing. And that package is needed because that gives us our totality zero. If you look back to what we had before, the x's and y's and z's, they cancel down to zero. It's the totality that's zero, not the individual things. The conservation of mass, of course, wouldn't have any meaning unless it was linked with non-conservation of space and time. Because we couldn't make any, we wouldn't even be able to say anything about conserved quantities unless we had non-conserved quantity to observe it. So this is why we invent concepts which package the parameters like momentum and force. And we use force because we need the second order for time. Now this kind of thing is what would be a minimal level packaging, and we make it universal by saying it's totally zero. And that's what we do with force. We say its totality is zero. And we do that with many other quantities, or make a similar arrangement with many others. And we can also do the same if we do vector additions of conserved and non-conserved quantities. We always get totality zero. Now we could do this, we could go on to do aspects of mechanics or electromagnetic theory or other aspects of classical physics in a directly mathematical form, but I'm not going to do that because that would take too much time. I want to go into quantum mechanics in preference. So I will simply reference 0 to Infinity Chapter 8 if people want to consult that kind of work. I've given an indication of how one would do it, but to get the details you need to read the book. What I want to do is look at some other aspects. If we look at that group of parameters, we see that the parameters are simply interchangeable abstract quantities. There is none privileged in any way. And this is quite remarkable because they make quite a different impression on our consciousness. We always think of tangible things, mass and charge and so on, tangible things we can get hold of, things we can relate to in that way. Space and time sort of more vague, more kind of abstract, but they're all equally abstract. None is more real than any other. And this is something we have to get out of the habit of thinking, that something is more real than anything else. They're not. They're all abstract. And we know that, in fact, that's true if we really think about it, because material objects are nothing more than interacting points. They're not actually solid objects at all. The illusion has just such a strong hold on the human psyche, it's hard to get out of this way of thinking. But we need to, because abstraction is the only route we can really take. And as I've already said, another aspect is that the physics at this level must have a total content of absolutely exactly zero. And we don't have to use algebraic terms to represent the properties and anti-properties. You don't even have to use the terms property, anti-property. But clearly there's some kind of cancellation, negation going on here. But it's not a simple one, it's not 1 minus 1, it's a more complicated structure which totals to 0. So it doesn't sort of disappear, it sort of zeroes itself in a more subtle way. Also, another reflection is that if those parameters are a group with such symmetrical properties, then we only need to know one of them to know the others, because the others will be automatic consequences. And we have all those strange things about space and time and other parameters which we haven't previously explained, but we've got a lot less explained to do if they're symmetric, because we can simply refer the explanation to the symmetrical properties. They'll emerge automatically from the group like kaleidoscopic images, and it's very like a kaleidoscopic image. It's like 3 dimensions. It's like something and 3 reflections in 3 dimensions. And that is not that is a true analogy, as we'll see. We can do various visual representations which are quite entertaining and interesting. For example, we can use colour. We can use colour to represent those 3 properties. We've got 3 primary colours, 3 secondary colours, 3 properties, 3 anti-properties. So we can use these colours. There's no unique representation. We can choose the colours arbitrarily. We can choose them to represent properties, or we can choose them to represent anti-properties, whichever we want. So this is how one could do it. This is a colour representation. For example, this could be, shall we call that space? Let's call this the identity element, it doesn't matter which it is. Let's call this the non-conserved property of space. That means that this must be a non-conserved property, so this ring round here must be time, because that's the other non-conserved property. So let's take another property of space, let's take its anti-commutativity. So that means that the space bit is anti-commutative here, and so this time of course is commutative. So it must be the other anti-commutative one, which is charge. So we know that space, time, charge, mass in this representation. No reason why we couldn't use the secondary colours instead as the primary ones. We'll switch them around, we can do anything we want. That brings home quite strikingly how at the same level everything is.
Maybe I missed something completely.
Yeah, we've got 4 rings, 4 parameters, 3 properties, right? So that is one property, that's another property, that's another.
Yes.
So let's say that's the conservation, non-conservation property in case of space.
Yes.
So this second ring must, that purple colour, that blue-purple colour, that must be time, because that's the only other non-conserved one. These 2 must be conserved quantities.
Why do you put them together like that?
You can put them in any order you want. You could switch the rings round, it doesn't matter.
In that?
Yeah, you've got to put them in some order. Yeah, I could have put them in a different order.
Okay.
Yeah, it's completely arbitrary. But I can actually identify which is which. See, these aren't together. I could have chosen this as the conservation property. Yeah. So it's completely arbitrary which you do. But it brings home how symmetric these things are. Totality will be 0. If you look at the colours, you add them up. You add the colours that way, the totality 0. Add them that way, the totality 0. Yeah. It's quite simple analogy, really, but
Yes, when you get it, it is. But
yes, it's quite nice though. Another thing we could use, so we've got X, Y and Z to represent our properties, why not use axes? Why not use a geometric structure with axes? Plus and minus directions, property and anti-property this time. So we could, and this is particularly striking because it shows the dimensional nature of this whole structure. So it's like the quaternion nature or the dimensional nature. Let me draw it without the axes, and the red lines here going to each of 4 corners of this cube, and you have plus x, plus y, plus z, plus x, minus y, plus z, and so forth. You have 4 different ones, and you can see there's 4 cyan ones as well, and what that could represent is a sort of dual group to our group, because in a dual group, in the group we have, we've got no minus x, minus y, minus z. So we've got another 4 quantities here which have the same structure. It's a dual group. It's not necessarily 4 quantities. We could have represented our group by these quantities instead of what we did represent. We could have changed all the signs. Now, in fact, there does seem to be some physical meaning to that dual group, because before I was able to get the version of the Dirac equation I now use, it became obvious that the Dirac quantities somehow switched some aspect of the real and imaginary quantities. So there was some aspect of the space and time which kind of switched. Time became real and space became imaginary when you use the Dirac equation, and I'll explain why that happens. And mass and charge similarly. That's why you got 2 energies, but you only got 1 charge in effect, and that kind of thing. And in fact, what I've done there is just switch these in the middle, or switch the plus and minuses round to get 4 different quantities. So these 4 are now no longer the mass, time, charge, and space we originally had, but a different set of quantities. Now, I don't think these are independent of the quantities we're using. They're just a mathematical variation of them, and that comes out when we actually work out what the Dirac equation actually does. But I did notice that quite a long time before I actually got to the representation of the Dirac equation I'm going to show you. Another one we can do is place them at the corners of a tetrahedron. This is quite neat because we've got a line there, and colour and anti-colour, if you like, primary and secondary. The primary colour and its appropriate secondary, red and cyan, green and violet, and blue and yellow. And in fact, we could switch it round. We could have the faces representing the parameters, because tetrahedron itself, of course, is a dual structure of another tetrahedron. This is my biological colleague drew this for me. So this is a nice representation of the whole structure. You've got the properties and anti-properties, like so, and you've got the 4 parameters. So that gives you a nice, neat expression of the structure, and that's my colleague Vanessa Hill drew that for me. If I put the 2 groups together, the actual original parameters, mass, charge, space, time, with the ones with the real and imaginary parts inverted, for these asterisk ones, I get a bigger group. I get C2 times D2. So there's a C2 symmetry between the 2, the simplest symmetry between the 2 groups of order 4, the two D2 groups, and we can do a C2 times D2 group structure. In fact, this is identical to the quaternion group. So we see again quaternions coming into this. Yet again, the whole structure can be structured on quaternions in different ways. We talk about the unreasonable effectiveness of mathematics in physics. This is very unreasonably effective because we can actually virtually reduce the whole of this physics into mathematics. I mean, look at two of the dualities, real and imaginary, that's pure mathematics and nothing else. Commutative and anti-commutative, that's pure mathematics. The only one that isn't obviously so is conserved and non-conserved. But almost certainly that can be reduced to pure mathematics. I don't actually know the exact reason for sure. I've got to guess about this. I've still got to work on this a bit. I've come up with one or two ideas, and one of them is that the time and space quantities are constructed from an incomplete quaternion group. In this algebra, I won't be able to discuss it fully till the 10th lecture, but in the 10th lecture I'll show that where the algebra comes from. And when I show that, I'll show that there's no such thing as complex numbers as a separate algebra. It's simply an incomplete quaternion group. So if you've got an incomplete group, that's those quantities that have got that seem to be the ones that are non-conserved, and the quantities that have got a complete group seem to be the conserved ones. I've still got to explore that possibility. I'm going to say this is what I'm going to explain in the last lecture. I'm hoping Bernard can come to the last lecture. I've just emailed him hoping he can come. My computer colleague who worked with me on working out a rewrite structure to create this algebra in the first place. Okay. Now, let's put all the mathematical structures together in this form. So let me talk about it in terms of Clifford stroke geometrical algebra. These are terms that we've come across in our second lecture: vector, bivector, trivector and scalar. This is space and this is vector. And you can see that it's got three subalgebras. This is charge, this is a pseudo-vector or a quaternion or a bivector, whichever you want to call it. And it could be represented that way or that way. And this has got just scalar subalgebra. And time, which is a trivector or pseudo-scalar, or complex numbers, that's got one subalgebra again. Now the important thing here is that if we define space by that, it automatically creates all that because of its products and multiplications. If we define charge by that, it doesn't create that. So charge doesn't create a vector structure. But if we combine these three together, if we combine charge with time and mass, or just with time, but with time and mass anyway, we will create the equivalent of a vector structure, because the missing vector numbers that are there can be made up from the complex numbers and the quaternion operators. So we can actually make up another spatial structure quite separate from space out of the rest of the stuff that's in the group. By the way, this looks a bit like if you look at it from, not from that point of view, but from the bottom upwards, this looks like a kind of evolutionary sequence. And in fact, this is what the rewrite algebra is talking about. But we'll see that much later on. So what we see is that we can create the missing ijk if we combine the rest of the parameters together as well as space. So if we put these three together, we've got another mathematical equivalent to a space similar to that ijk, which is this ijk. Now this is not a space physically, because it's not a single quantity, it's all different ones. And it will never be measurable or observable as one. However, it's mathematically the same. And so mathematically, we've got two spaces. This is like an anti-space, if you like, because it's the thing that zeroes the space, the real space. So it incorporates everything that is not space and allows us to equate the totality of that to zero. If you take space as the identity element, then you would get that, it's always positive for the identity element. The anti-space total would work out as that if you added up the other three terms in the structure. We could do the same for mass and charge, but because we don't observe them directly, it's not as useful to do that. So again, the structure seems to be telling us that the universe is a conceptual nothing, a zero, a totality of nothing, no defining characteristics. We can't even decide whether we should describe it ontologically or epistemologically. And this has caused a lot of philosophical argument in the past, but we can see where it's coming from. And there isn't any way of deciding that from within a structure that's totality zero. And again, as I've mentioned, the factor 2 that appears everywhere is because any defined aspect of nature always produces a mirror image of itself, which then negates it, zeroes it. And I'm explaining again, emphasizing again, that the totality of the universe is absolutely nothing at all. And it's no longer a startling concept, that. We may first think so, but if we're looking at it from the outside, we can never see the whole picture. We only ever see a partial picture. And because we see a partial picture, it never looks like nothing to us. And we will never get a handle or an idea of what that nothing really means. Even if we say, I take that from that, that's not a true nothing, it's only a sort of partial idea of nothing. We can never get really close to zero. And as I mentioned, because we've got a group symmetry and not just 1 minus 1, it's clearly a more subtle nothing than we originally might have imagined. But if we have this nothing, then it forces to take a holistic view of the universe. Because we've always got to get nothing when we add it all up, we've got to do it in some way that is kind of holistic. And we will see that comes out in the quantum mechanics that we do as a result. What we now have to do is put the package together. How do we get this package together? And this is very interesting, the way this works. How do we get a coherent, unified system out of this package of things, and how does it become a nothing in the package? So this is what I would call the first level of complexity. If you've got the basic, and then you've got to package it together, and that package is the first idea of complexifying nature. Well, I say we've already got the mathematics. We've got nothing to worry about. We've done the mathematics in lecture 2. We take the Clifford algebra approach, for example. We've got 2 vector spaces. This one here, we don't really have these, but we can make them up out of those. This one, we have those. So we've got the complete structure. But we can put all that stuff together and create a package. And we've done that kind of thing before. We did it in lecture 2. And that's what we got. We got plus and minus values of that structure. 32 objects there. Multiply them by 2, 64. And quite simply, it's a binary combination of all those things. Now, we could have begun like that. We didn't need to, there we began with 2 complete algebras, but we didn't need to do that. We don't need all the algebra to do it. We only need, for example, that. If we started with the 4 parameters, we could have put those together. By multiplying them out in every way possible, we would have got that total algebra. Those are our 4 parameters with their particular algebras. Then we would have got something like that. This asterisk, you can work out the significance of those afterwards. That's left for an exercise to the reader, what those mean. Here I've changed it slightly. Instead of having 2 vectors, I've got vectors and quaternions complexified. But we know that's okay because we've done that in the second lecture. We showed that was the same as the double vector algebra. Now, this is where we have already seen these were a group of order 64, and we've got 8 generators of the algebra. Or we can generate it from 6 generators, nice and symmetric, IJK and IJK. However, that's not the simplest. That's not the minimal. It's the most perfect symmetric. That's the most perfect and symmetric, but it's not the minimal. Nature doesn't go for the most perfect and symmetric, as we know from the Higgs mechanism. It goes for the minimal. And the minimal number of generators for a group of order 64 of this kind is 5. And we've done that before. You may recall we've done that, and they tend to look something like that. And now you may realise what the significance of the asterisk terms was. Yeah, they were the generators. They weren't the generators, but they were a set of generators. Now, if I put all 64 terms in a different order, in this way, what I can see and I think I've done this before, is that we get that 5 there is a set of generators for this algebra. I can multiply all them out and get all the terms when I multiply them every way, inside out and the rest. Those 5 are a set of generators, those 5 are, and in fact we have 12 5s of generators. Nor is that the only way we could do it. We could shuffle all them around and get many more sets of 5 generators in lots of different ways. Even as they stand, they've got multiple physical meanings, which we will learn about later. But we can see that what I'd like you to see, it will not be completely obvious here, but what I'd like you to see is that all these sets of 5 have got the same pattern. Whichever way we do it, they've all got the same pattern. And that pattern is, you see these 3 blue ones here? They are multiplied by the same red object. So those 3 are still symmetric. Those rotation symmetry, rotate one into another simply with the blue terms and ignoring the red. Those are rotation symmetric. The blue space is rotation symmetric still, as space must be. And that is what we call space. If we now look at the red objects, we see that they are not symmetric any longer. The J is on its own, multiplied by 1. The K is multiplied by complex I, and the red I is multiplied by I, J and K. So we have lost the symmetry of the red ones. That's the sacrifice we've made to get the minimum number of generators. We have 2 spaces, the symmetry of one has been lost and the symmetry of the other one has been preserved. And that's the only way we can actually get 5 generators with all these terms in. But if you look at any of the other sets of 5 generators, it's the same structure. You can, of course, switch it so that the blue ones lose their symmetry rather than the red ones. But one of them has to. This is what we get. Something like that will be our generators. So that doesn't appear to be as symmetrical as that, or just that and the other vector, ijk. But it contains the same information and the same symmetries. It's just that they're packaged differently. So as we see them as a package, the symmetry of one is lost. But ultimately it does have that symmetry. And it's this packaging always that creates broken symmetries. Broken symmetries isn't some mechanism on high coming down, breaking symmetries. It's building up from below and packaging. And that's how we get broken symmetries. I'm saying the process is dual. We could reverse the process so that the blue ones were broken rather than the red. We could have a distorted space-time. And in fact, I've investigated this using what's called Finsler geometry. And in fact, it's possible to do it. It's inconvenient to do it, but you can do it. And then you preserve the symmetry of the red ones, which are the charge ones. The way we have it is that the symmetry of the 3 components of charge and their interactions seem to be broken when we observe at the level of observation. And that is when we package with space, because we can't observe till we package with space. So we have to break one symmetry to preserve the other. That's the only way we can get the minimal generators. Let's spell it out this way. I've got time, I've got space, I've got mass, I've got charge. What I'm going to do is take the 3 charge operators and put them somewhere down here below. So I've still got the same 8 there, but now I'm going to package that one with that one. I'm going to package that one with those, and I'm going to package that one with that. And this begins to look like the kind of broken symmetry that we're familiar with in physics in the standard model. Again, if we package space and charge, and time and charge, or some component of charge, we're not going to have the original concepts any longer. We're going to have a packaged concept. And I'm not going to get into detail how this happens, but essentially I could put quantities below those. These are just scalar quantities, scalar numbers, because we've got no scalar values for these. This can be anything you want. If I put scalar quantities below these, I can now say I will call this quantity with that characteristic by the name energy, that one by the name momentum, and that one by the name rest mass. or invariant mass. So the quantities are defined by their algebraic units, not the scalar values. So this is the first appearance of these conjugate quantities. So the energy comes where the time was, the momentum comes where the space was, and so forth. And it would seem that superposition of two sets of parameters with different characters to create generators for the group actually creates these quantities for the first time. Because we didn't have them before, we only had space, time, mass and charge. But now this first level of complexification got these new quantities. It also simultaneously fixes quantization and relativity as fundamental. Because when we package these together, both those things will emerge. This structure is what we would normally describe as phase space, but it's not independent of the spaces that created. This is very interesting because this is what we find in quantum physics, that the conjugate pairings time and energy and space and momentum are not really independent. And that's because this and this are partly created out of the original object. So they're not going to be independent of the original object. You can only have commutativity for totally independent objects. Things that are related fundamentally can't be commutative, they're anti-commutative. So this is why we get anti-commutativity of these quantities. This is of course what we get in Heisenberg's uncertainty. One could derive the uncertainty principle in a more formal way, but this is giving us the idea of where it's coming from. It makes perfect sense in this structure because we wouldn't expect quantity and the derived quantity to be independent. I'm saying that physics has to operate in such a way that the total package of all information is zero. And so this is the object we've created by packaging it all. And I'm going to say that this, whereas each of these has some norm 1 or minus 1, the package has norm 0. It's a 0. It's like its Pythagoras structure is 0, its norm is 0. And here we recognise, if we multiply all this out, what we will get is Einstein's energy momentum mass equation, E squared minus P squared minus M squared equals 0. Of course I'm assuming C equals 1 and H cross equals 1. And this is a nilpotent structure. We talked about nilpotence in the second lecture. This is a nilpotent, square root of 0. And that's just a classical equation at the moment. So, from a fundamental point of view, what we're doing by creating a nilpotent structure is actually creating something that's got 0 extension. It's a point. To create a point in space, we have to have two spaces of a different nature. We can't create a point in space by just saying, oh, we'll have a point there. Space can't do that because it's non-conserved. Won't have it. You've got to create it this way. It's the only way you can do it. So we combine two spaces, space and antiphase, to cancel, if you like. This is a descriptive way of looking at it, and create a spatial extent of 0. And the two spaces, as we'll find out later, actually have the same information in them, because of course they combine to 0. So it's like 1 and minus 1 combining to 0. It's got the same information. It's just differently organised. So these two spaces have the same information, differently organised. And that duality is a theme throughout the whole of physics. And this observed space, the observed space as we understand it, will become multiply connected because we've got two spaces with a singularity. I'm going to call the other space vacuum space. There's our singularity. That's our multiply connected space. And again, as we've seen before, we have to do a double circuit of that to get back to where we started. And this is because it's only in one of the spaces half the time, if you like. That's a nice descriptive way of looking at it, which is what Zitterbewegung is. The charged singularity is itself a multiply connected space, so that's why it has spin half. So we can say that the 5 group generators are the most efficient packaging that we can do of this structure. We should be able to use it to generate the physics of fermions, which is the only really fundamental thing we know about in physics. There are only fermions and fermion interactions. At the moment, that's all we know about. Bosons are fermion interactions, part of fermion interactions. So there's only fermions and the relations between fermions. And we can actually do this in a quite a remarkably transparent form. We'll do a lot more about it in the next lecture, but in this lecture here I'm going to just do it approximately. So this is our first equation, and I can gather the vector terms there in a single momentum term. That's another thing that we will often do. And what I'm going to do is just take a shortcut here and do a canonical quantization such as we do with the Schrödinger equation. And I put I becomes d by dt. Of course it would be h cross if you had h cross being other than 1. And p equals minus I del operator. And I'm going to have a phase term like that, and I can rewrite that equation as that. It doesn't have to have any physical meaning, I can just make that up and do that. And it would be the same as that. This, I will show, is the same as the Dirac equation for the free electron. This is the quickest, simplest way of deriving it. We simply square root that equation and quantize that bit. So if you like, this is showing the simultaneous application of the dual space. So if you like, what we might call the amplitude term represents the localized real space of the point particle, and the operator acting on the phase factor represents the variation over delocalized vacuum space. I won't go into detail about that, but that's a physical way of looking at it, if you like. That's showing both spaces acting at the same time to give us this expression. Now, in fact, the phase factor doesn't have to be that, it can be anything you want. And in this form, it's actually, this is the phase factor you would get for complete variation in space and time. Thing that without anything holding it back, complete variation. So we will see that amplitude and phase are not independent information, they're the same information, nor are they independent of the operator in this formalism. We'll show that there is only the operator, there is nothing else. So everything inside is inside the operator, and this sets up what we might call the non-conservation conditions for space and time. And these create the conserved quantities. I will also show that it's an angular momentum operator. I'm saying not only do we create the energy momentum rest mass thing, but actually we change the charges as well. So I've changed the non-red ones, the blue ones and the black ones, but now I'm going to change the red ones, because the red ones are still charges. And this one now becomes associated with a pseudo-scalar term. And I say that has the characteristics that I would call a weak charge. This has now got a vector character, and I call that sort of the strong charge. This one is left on its own with the scale, and I call that the electric charge. And what I would say is that if you, I can't justify this totally yet, but you can see the indication of it here. That you can only justify it by going through the quantum mechanics, which I will do. But in fact, you can see the indication of where it's going.
Yeah. When you first showed me that in 2002,
Right.
and I was staggered.
Yeah.
Because it's got exactly the right structure.
It's got exactly.
Strong charge has got three types of charge.
Yep. And
Just
we
in there.
can go through the quantum mechanics and show it works in the most powerful way. So these are these SU2, that's the weak, SU3 and U1. Those structures are related to that. 2-component pseudoscalar will give us SU2. A 3-component vector will give us SU3, and a single component scalar will give us U1. And they're all contained within the structure. Now I need to return finally to these slightly unresolved issues. So what is the nature of the dual group to these? Well, why did we have this stuff here? Essentially, it's because when we package this, it's because we've got the K, I and J in front that we're actually changing from real to imaginary, imaginary to real, because we're multiplying them by an extra term. So it's these things that are the dual group. And we could get the same thing, that's writing Einsteinian relativity, space, time and proper time in a nilpotent form. Very convenient thing we can do. And the final term is it will be a quantized angular momentum, maybe spin in fact. So we can make the group of order 8 involving these. Yeah, that would then become the quantized space. I had a student from a long time ago who's also investigated other groups of order 8 which might be related. So this is his name's John Valentine, but it's a student from long ago who's been interested in this for a long time. So this is a different eightfold structure to the parameters and the duals. We can use the we can use the units of the parameters to get a different eightfold structure, and which is very close to Penrose's twistor structure, 4 real and 4 imaginary parts, though he doesn't quite have enough structure in his, in my view. He needs 3 plus 1 involved in it as well. And here I'm emphasising that symmetry breaking isn't because some Deus Ex Machina comes down above and says we will break symmetry. Combination that reveals broken symmetries. And this is arranging the parameters as algebraic units. And this is, in fact, an octonion mapping of it. You can map them as octonions. And all the ones that are anti-associative have no...
G's in it? I'm sorry, I missed something.
This is octonions. This is the... Well, I'm using... This is mass, space... strong, electric, weak, time. And there's 3 dimensions of space. I could have used the algebraic symbols, but I used those instead. And we can map those onto an octonion structure. But the thing is that the anti-associative bits don't have any physical meaning, as I've found. So it works quite well. That's only an interest to show that you can do an octonion structure as well if you want. Though it's really a broken octonion. Now let's go back. This is the final thing I want to do. The extraordinary result that we predicted as a consequence of Noether's theorem. The fact that type of charge, conservation type of charge, electric strong weak, baryon and lepton conservation was the same thing as the conservation of angular momentum. A really bizarre, strange result. And I asked mathematician after mathematician, could they prove it? No, they couldn't. And nor were they interested, but they couldn't prove it if they were. So how can you possibly do that? It's also the same, of course, as the rotation symmetry of space. Well, eventually I worked it out. When you look at angular momentum conservation, it isn't one conservation law, it's 3. It's conservation of magnitude, conservation of direction, and conservation of handedness, whether it's left or right. And if you realise that it's 3 conservation laws, these are completely independent, hence why gyroscopes work and so forth. So we have to conserve these separately, whether we like it or not. And when we do so, we realise these conservation, the symmetries we require are the U1, SU3 and SU2 symmetries. That we have electric, strong and weak charges. So in principle, what we're saying is that spherical symmetry is preserved by rotating system, whatever the length of the radius vector, that's U1, whatever system of axes we choose, SU3, whether we choose to rotate the system left or right-handed, SU2. And that's why that thing works. So conservation of charges, the conservation of spherical symmetry for the point source, and that's what it's telling us. Effectively, the strong deals with SU3, the weak deals with SU2, and all deal with U1. But only the weak, only the electric only has U1. All the others have it as well. I think that's my last slide, except this one, sorry. There's one more. So each has to be conserved independently because of the direction, handedness and magnitude of the angular momentum. I think that's an amazing result. It took me about, 15 years or something to find it, but I eventually found the reason for why that was so. Okay, that is the last one.
So the absolute prediction is that a proton will not decay.
Absolutely. It will not decay. Okay, thank you. Yeah, thank you.
Next one week from now.
So just to go back once, if you don't mind, just a little
Sure.
side. So actually the quaternion algebra
Yeah.
has allowed you to represent
Yeah.
the Klein-Gordon expression,
Yeah.
using the old-fashioned
Yeah.
language for you, in a different way from the original linearization that led to the
Yeah,
issue
it's a
of
di- it's a-
type spin
Yeah,
algebra. But you've driven it entirely from this nil potency requirement.
I can do it entirely from that, and not from any other requirement whatsoever. And this, in fact, if I would quantize both expressions, I get Klein-Gordon.